people still arriving in the presentation room, and we have a whole bunch of people that are logging on to the virtual version of this that will hopefully be good, but never as good as in person. My name is Dave Whitmore with Vector Construction, Vector Corrosion Technologies, and I'd like to start by just welcoming everyone here this morning and for taking time to come out and see this very, very interesting project and a little bit about the history of the bridge and the design of the repairs. And then after the presentation, we're going to have the opportunity to go and do a site visit. We'll do a short safety orientation with everyone here because I know not all of you are oriented to this particular site. We'll do that walk around. You'll be able to see all of the different aspects of work that are going on the site. And then we'll come back and we'll have a light lunch back here in this room at the end of that. Okay, so my name's Dave Whitmore. I'm here representing Vector Construction, Vector Corrosion Technologies, and it's a pleasure to be here and looking forward to the site visit as well. And I'm going to talk more about the construction and the specific details of what's going on. So we had a really good overview of the history, the design, the whole design intent, all the specifications and drawings. And we're going to talk really about the concrete repairs, specifically the corrosion protection that's incorporated into those repairs. And there's a couple of slides in my presentation that I'll probably just skip over, like the next one here, because you've already seen some things about the bridge. So I wanted to start by just touching on that probably everyone in this room and probably everyone that's online has gone to a concrete bridge that's more than 10 or 20 years old, and you've seen some issues related to corrosion because of the reinforcing. And if it's a pocket, you know, those structures are getting old enough, we see tons of those kind of structures corroding. Arnie touched on this in his part, so I'm not going to spend a lot of time. I'm going to use a few slides from this report, and if anyone wants a copy, you can let me know. But I had the privilege of being involved in the Strategic Highway Research Program project was called R19A, which had to do with design of bridges for 100-year plus service life. And it also had to do with extending the life of existing bridges to get 100 years or more. And this is clearly in that latter category. And one of the figures from that report is this one here, which talks about causes of corrosion of steel and concrete. And, you know, for most structures, not old structures, we're dealing with chlorides. As Arnie mentioned, we're also dealing with carbonation in this case because of the age of the structure. And if anyone wants to know more about those processes, we can talk about that later. For some of you that aren't interested in the specifics of why these things are happening and whatever, you can just kind of tune out right now and come back in 5 minutes. But I want to walk you through a few slides just to try and give you a very high level explanation of what's happening inside the concrete and why you see all these effects that we see over time. Including the effects related to doing partial repairs and leaving chloride contaminated concrete. So this is supposed to be a very simplistic graphic of reinforced concrete bridge deck. Okay, you've got fresh concrete and it's highly alkaline, and you'll have the formation of what we call a passive oxide film. And if you want to know what the chemistry of the film is, it's a combination of Fe3O4 and gamma phase of Fe2O3, which no one's going to remember. And that film is stable in a high pH chloride-free environment, and it will last well over 100 years. You'll see lots of evidence of where this protective film is still in place there out on the bridge here, which is more than 100 years old. But if the concrete becomes contaminated with chlorides or the concrete surface becomes carbonated down to the level of the reinforcing steel, the chemistry of the concrete is no longer compatible with maintaining that passive oxide film. The pH isn't high enough if you've got carbonation, or the level of chlorides exceeds a threshold for corrosion to initiate, at which point this passive film breaks down. Okay, until that happens, you won't see any signs of corrosion. When that happens, corrosion is an electrochemical process, so the iron in the steel starts to dissolve, giving off electrons. If there's chlorides there, that tends to act as an accelerant. And the corroding areas we call an anode. And you're going to get a little bit confused because we're going to talk about using anodes to protect the steel from corroding. But any piece of metal that's corroding, that's giving off electrons, is by definition an anode. So an anode is an electrode that's giving off electrons. And the corroding steel at this location where you have chloride contamination is an anode. Those electrons have to go somewhere. Okay, they're being generated by the corrosion process. They need to go somewhere. And so they will flow within this network of steel that's inside the structure. In our case, the Melan angles in this structure, but normally the rebar. They're typically going to flow to an area which we call a cathode. And at that location, they're going to react. And these electrons that have flowed down here to this area that has no chlorides, they're going to react and they're going to form more hydroxyl ions, which, if you remember back to your high school chemistry, that is how you measure pH or alkalinity, right? So you're actually generating additional alkalinity at the cathode where the electrons are flowing to. Okay, and this steel down here is being protected. So a cathode is an electrode which is receiving electrons. And because it's receiving electrons, it is by definition protected and it cannot be corroding. So from a cathodic protection point of view, which you're going to hear about later, as long as we can make the steel a net receiver of electrons, then the steel by definition can't be corroding. Okay, it's only when the steel is giving off electrons that the steel is actually being converted from being iron, a metal, into corrosion products. Okay, no one outside of this room, and most of you in this room, care at all about what I just said. Okay. DOT doesn't care about what it said, whatever, but they do care about that these corrosion products eventually, first of all, react with hydroxide typically because we have an alkaline material and oxygen in the environment, and we form Fe2O3, which is a normal red rust that you're familiar with. And because that material occupies more volume, it's less dense than the steel is itself, that creates internal cracky pressure in the concrete, creates cracks, creates delaminations, spalls, if you let it go. So people are generally only concerned about the physical impact of this reaction that's happening inside the concrete. And that's okay, because that's ultimately what's causing the damage. But it's important to understand what's causing that physical change in materials. Okay, so I said very simply that, you know, the chlorides getting in there cause this to happen. That's true. Or if it becomes carbonated, that will cause this to happen. But there's really one other part of the equation that you can see very clearly when you go and do certain types of measurements on site. If you go and do a corrosion potential survey, like Arnie mentioned early on, and you do a corrosion potential measurement of a piece of steel that's in chloride-free concrete or not carbonated concrete, you're typically going to measure a potential that may be around -200, maybe even a little more positive than that. Okay. If you measure the potential of the steel in chloride contaminated concrete, you're going to measure a more negative number. Okay. These numbers that I've put on the screen are simply picked from the ASTM standard for the method. You know, if you're -200 or more positive, the steel is typically considered passive or not corroding. If you're more negative than -350, the ASTM standard says that there's a high probability that corrosion is occurring. But the point that I want you to walk away with is that there's a difference in voltage between here and here. And the reason that exists, so the reason this potential is more negative is because of this reaction here at the top. The iron is dissolving and generating electrons. The electrons, by definition, are negatively charged. They will shift the potential to be more negative, okay? Because they're negative, the electrons want to flow to something that's more positive. So they're going to flow to anywhere that is more positive to where they're being produced, okay? In this very simple graphic, I've illustrated a top mat of steel and a bottom mat of steel in a bridge deck, which is very typical. You know, you have chloride contaminated steel at the top, not chloride contaminated steel at the bottom. You'll have a macrocell current that flows from the top steel to the bottom steel, like you see here. You will have the exact same thing happening on that bridge deck between the top of the bar, the top bar, and the bottom of the top bar, typically because there's a difference in the chloride concentration, even in that 1/2 inch or 3/4 inch distance, right? Yes, sir.
So when you see, you know, like a full depth hole where you've got really nasty rebar on top and the bottom, are the cathodes just elsewhere in the grid, basically?
Yeah, so if you have a nasty hole, like you said, you have good terminology here. You're the vintage concrete guy, right? So it's hard to generalize, but it could be, for example, a situation where you have a crack in your deck and you've got chloride contaminated water seeping through that crack, and both the top mat and the bottom mat of steel get contaminated with chlorides at that crack location. Or it could be a construction joint or something similar. And at that point, those are both going to be acting as anodes. And in that scenario that we just painted, the steel immediately to the right or left of that crack is probably going to be cathodic, not corroding relative to the crack.
Why when you fix it, then the stuff that's nearby gets better.
Exactly. When you fix it, it just pushes the problem further away, right? And we'll just get into that here in a second. So yeah, so these voltage differences within the structure is what drives the corrosion cells, and ultimately we can use them if we understand what's going on for protecting the concrete as well. Okay, so when we do a repair, when you do a repair in a perfectly ideal world, we want that repair. So if you look just below the graphic, so the graphic's showing a repair in a piece of concrete. You got two different shades of gray illustrated by the concrete and the repair material. And the first line of green underneath, says the ideal repair material does not shrink. The repair doesn't shrink because that's going to create cracks at the edges or maybe cracks within the repair itself that obviously chlorides and whatever can get down in, and your service life will be very much shortened. And we want that repair to be compatible with the substrate. And when we say compatible, we want it to be able to move with and work with the concrete in all ways, both physically, like in terms of modulus. We want the stiffness of that repair material to be similar to the concrete. So when you load the structure and unload the structure, we don't get the load being preferentially either put into the repair or into the substrate. We want to have the thermal expansion coefficient of that repair material to be similar, so that when it heats up in the summertime, the concrete and the repair heat ups and they expand similarly and contract similarly in the winter. That's the reason why most polymer, like epoxy mortar repairs that have been done in exterior environments fail, is because you have a big difference in thermal expansion coefficient. And then we're going to talk primarily today about electrochemical compatibility, because if you're repairing that repair with a piece of concrete that has no chlorides in it at all, and the rest of that concrete that's left here is still somewhat contaminated with chlorides, then we're going to create some type of electrochemical incompatibility, i.e. voltage differences that are going to lead to corrosion starting the day you do that repair. And so, you know that if you go and do repairs on a structure, this is a picture from a VDOT project from a number of years ago. They've identified the repairs, they've done good quality repairs. The repairs themselves will be durable. There's no chlorides in the repairs. You're not going to have to worry about that. But the localized repairs by themselves, if you're leaving chloride contaminated concrete all around, is going to lead to secondary corrosion. People say patch accelerated corrosion, whatever, but the areas adjacent to those repairs, there's going to be sharp voltage differences, and you'll tend to see corrosion occurring at the areas adjacent to where you've done first round repairs. That's a bridge deck from Connecticut. This happens to have about 4 or 5 different generations of patch repairs on the same bridge deck, and some other new ones that are marked out for repair. But we also need, so if we want to deal with this problem holistically, which Arnie kind of mentioned earlier on, we need to think about other sections of the structure that are between the repairs. We have stuff that's directly adjacent to the repair, which might be impacted by the repair. And then we have the stuff that, maybe several feet away from the repair, but it's chloride contaminated over there and it may be corroding in and on its own. And we need to think about that. And these pictures I've shown you in my graphic are all showing a simplified bridge deck, but the exact same thing happens on bridge substructures. This is actually Florida DOT bridge, and you can see good quality repairs were done on those piers in a marine environment, and you can see across the top of both of the repairs areas of additional delamination's been marked out. Okay, so we've already kind of jumped to this part. If we're doing a repair and we're repairing a portion of the concrete with chloride-free material, and we're leaving chloride-contaminated material adjacent to it, we're going to create a situation where we have a voltage difference, a potential difference between those two areas, and that is going to lead to corrosion that's in a way going to be driven. I mean, it's going to occur anyway, but it's going to be driven worse because now you've coupled it with a material directly adjacent that is more positive than what it was. And you can pick up all of this by going and doing the detailed kind of half-cell corrosion potential survey type data that you want. Now, we can use this problem and we can actually kind of mitigate it, or at least reduce it, by incorporating some type of artificial anode into the repair. And sample over. You'll see a few of these out when we do the walkthrough, but so illustrated in the graphic is a galvanic anode, and you'll see some galvanic anodes like this when you go out to the job site. That anode's electrically connected to the steel inside the repair area. The closer it is to the edge of the repair, the more effective it is. And this works because the anode, inside the anode, is zinc. Zinc is more electronegative than steel. So if you look at a galvanic series that's shown on the right-hand side, you got steel here, and you got zinc over here. You've got generally about half a volt, between half a volt and 1 volt difference in voltage between zinc and steel. And coupling this zinc anode to the steel puts something into this localized environment that is more negative. And so once you couple these things together, current is going to flow from whatever is the most negative towards areas that are less negative. And yes, it will protect the steel that's inside the repair, which isn't really necessary because it's not going to corrode anyway, but it's going to be more negative than the steel in the immediately adjacent area. And so current is going to flow, to those areas. Now, obviously, if you put a small anode like this in, yes?
What's the radius?
There.
And I'm just going to every single anode you have, so.
Okay, so obviously, if you have the discrete anode like this, there's a limited area of influence as you move further. You have the voltage difference. Let's just say it's half a volt, just to pick a number, okay? Or you could say 1 volt, whatever. The influence of that is going to diminish as you move further and further away from it. It's still going to, you might have the same voltage difference, half a volt or 1 volt difference, but the further and further you move the steel and this apart, the more resistance there is. Arnie mentioned that, the more resistance there is in the circuit because of the distance, right? And so the effectiveness of this anode, although it's still going to pass current, from me to you at the back of the room, the amount of current that's going to go to steel that far away is going to be negligible, right? And more of the current's going to go to steel that's within the first couple of feet. So if you, usually the area of influence, you're going to get about 50% drop in the current, usually within about the first 18 inches, okay? If you think about 3-foot radius, you're down to really low kind of background levels. And so you're going to see spacings that are usually in kind of 2 feet, maybe as much as 3-foot center range. And that's to get current coming from both sides to a central point that'll be equivalent to being close to the anode itself. Okay. So Out on site, when we go there, you're gonna see a whole bunch of different things. You're gonna see a bunch of concrete repairs that are in the process of being done. Ward Construction is doing all the shotcrete for that, and you'll see that. You'll see a lot of repairs of the corners of the arches. You're gonna see some board form thing being reestablished, some new steel, some discrete anodes, some two-stage anodes, some distributed anodes, some metallizing, and there's a bunch of crack repairs that I don't know if we're gonna see much of that today. So the condition of the arch, Arnie showed you some different things, you know, a lot of issues around the corners. The big issue here, let's see if this video plays. So there's a joint up there, and after rain last week, Nick took this video and you can see that there's water leaking down. The joint seal has not been installed in this joint, so don't worry, the bridge is going to be fine. But this is just indicative of what has led to the problems that you're seeing out there, is that you've got joints, you've got leaking joints, you've got water leaking down at these specific areas. The next video shows where that water is leaking down. You can see it going out along. This is from a rain last week. See, it's running down and then it's running along the corners of the arch. It's coming out obviously where there's cracks, and that has led to, you know, a lot of the issues that you see out there where, you know, it's pretty much, I would say, mostly stuff that's coming from the deck. It's coming down at specific locations, and in locations that are directly exposed or underneath where they've been exposed for years to running and dripping and leaking waters. You know, the amount, you know, concentration of repairs is, you know, large areas, and other places that are removed from where these areas of leakage are, there's little or no damage, right? So it's very much correlated with the water, as Arnie said. So in terms of the repair here, the first step in the repairs is repairs rectangular and relatively uniform in consistency. Photograph. The repair, the material that's being removed is largely, at least in the repair areas you're going to go and see today, are as being replaced using the wet shotcrete method. So hopefully we'll get to see, or at least be able to peek down and see them spreading. Certainly see those that are prepared and ready. So we're doing wet shotcrete for the repairs. Building up the excavated area, flush with the surrounding concrete. Some of these repair areas are quite deep, you know, 4 to 6 inches is pretty typical. And then, as was mentioned before, in areas that are visible, the board form finish is being reinstated. And I think they're doing a fantastic job of this. You know, it's actually all being done by hand, and to match the board finish on, you know, the adjacent areas to the repairs, right? So quite labor intensive to do that, and I'd say it's an artisan, but it looks good.
So was the extended time for the repairs of the bridge caused by unforeseen deterioration that caused the extension of the time?
I'm not sure. I mean, certainly there's a lot of repairs to be done. I mean, there's been a whole bunch of other stuff with the deck replacement and that too. I know they're pushing hard to try and limit the, you know, schedule extension, but I'm not exactly sure where the total quantities are going to end up relative. Certainly in some of the early areas, the quantities were high, but like I said, some of the areas, you know, the repairs are more concentrated too, so that may not be typical.
It's a star subject.
Yeah. And there's probably other people in the room that can answer that question better than I can. Yes, sir.
just a quick question. I don't know if someone mentioned, what's the depth to the Melan, rebar? And then, what the repairs is showing there, gravity is always on.
Yes.
So I mean, how do you ensure that you're getting a good bond with where you're doing a repair that's, vertical?
Right. So the distance to the Melan, is 4 inches,
Varies, yeah.
4 to
It's
6,
Typical, but it's 2 inches up to.
6, 8.
Yeah,
Foot?
or a foot, depending. And every overhead patch is being anchored with, anchorages,
Okay,
mechanical anchorages.
okay.
This was during a mock-up to show the board form finish, there's no rebar in there.
Yeah.
And they chipped it back out.
Oh, and it's chipped back out again?
Yeah.
Okay.
Okay.
There you go. You're gonna see areas when we go out there and the anchors are installed, the supplemental reinforcing that's just within the repair area and doweled into the adjacent areas. You're gonna see that. Is that what you?
This was gonna say that was a mock.
Okay, okay, very good. I still think it's really good in showing the thing. So we'll talk just a little bit, again, going back to the Sharp document, options for currently corroding structures. Everything from doing nothing, which is obviously a lot cheaper, but doesn't last as long, through to, some of the more involved things like cathodic protection, which we're going to talk about here today. They're doing some of the other things here too, in terms of partial removal and placement, as well as treatments like coatings. But in terms of, we're going to see 4 different types of corrosion protection systems out there when we do the walk around. And I'll just walk you through. You're going to see discrete anodes, like what I just I held up earlier and showed you. I'll explain that in a second. You're going to see distributed anodes. Can you hold one up there? Okay, this is a small sample, but they're much larger than this, the ones that are being installed because of the design life for this project. And then I'm going to show you in the I'm going to walk through, because those two are done in one type of repairs. And then there's anodes that are installed in drilled holes, which we'll come to. And then there's metallizing, which has already been mentioned, which I'll show you separately. So Arnie showed you one of the details for like the corner repairs. You can see the similar thing here, and in the repairs, the discrete anodes, for the people that are online, they can't see my pointer. So at the top and bottom of the repair, there are 2 discrete anodes, basically that are intended to protect the end of the Melan steel where it protrudes into the adjacent concrete. And then along the length of the Melan steel, what's shown in yellow on this drawing are the distributed anodes that run along the length. The discrete anodes, you've seen them already. I don't think there's anything that you need to see there. The distributed anodes, you can see they are kind of like the long strips that are running just below the upper steel angle and just above the lower steel Melan angles. One of the things that's being done here, and here you can see the typical, you can see the saw cut repairs, the concrete removal's done, this concrete's been sandblasted, the exposed Melan steel has been sandblasted and coated white with an epoxy coating. That's to protect that surface so it's not drawing all the current from the galvanic anodes, because it's going to be in fresh concrete anyway. It's to force the current to go to the back side where it's not coated. So the white strips there are the Melan steel angles, in this case, that are partially exposed. And the green steel that you see is epoxy coated rebar that's been installed for crack control and doweling of the shotcrete repairs back into the substrate. Okay. Here's the same thing, but you can the anodes are installed. So you can see the distributed anode installed underneath the Melan angle going along there, and you can see discrete anodes at the 2 ends, and I think it's more clearly shown here. So here you can see all of the steels installed. The distributed anode is just underneath the Melan angle at the top, and there's a similar one at the bottom because this is a whole face repair. And then at the ends of the repairs, you can see the discrete anodes. And in very small repairs, and I don't know what the distance was, but in the very short repairs, there's only the discrete anodes at the two sides. So on the bottom right-hand corner here, you see a small repair where a section of Melan steel is exposed and just the discrete anodes are installed there. Okay, you're going to see a couple places out there. I know one on span 2 when we do the walk around. Where you'll see this kind of detail where they've had a certain amount of corrosion of the existing Melan steel. They're putting in supplemental reinforcing. Okay, this is for structural reinforcing, and they're using stainless steel rebar for that. And so you'll be able to see that on at least a couple of the repairs that are open and getting ready to go back in for the repairs. Yes.
Are there any concerns with that stainless, that close that galvanic anode?
A small amount of current is going to go from the galvanic anode to the stainless, assuming it's electrically connected with the other steel, which in the end it probably will be. It's not going to draw very much current from it though, because stainless steel doesn't, it's not a very good cathode. So basically, because of the nickel in it, it doesn't actually take very much current compared to normal black steel.
We go through great lengths to like cover every galvanized piece of embed next to stainless steel in the bridge deck, right? So,
Yeah.
I mean, here we have this giant anode sitting right next to stainless steel.
Yeah. So a small amount of current from that anode is going to go to that steel. It's a very large, compared to your situation where you've got galvanized and a large mat of, let's say, stainless steel, you've got a different ratio of kind of anode to cathode. Like the amount of zinc that's in that galvanizing is going to be really quite small compared to the total amount of zinc in those anodes. But yes, a certain amount of it will be consumed by going there, but it's relatively small. The anodes need to be electrically connected to the steel in order to work, okay? And so normally for normal rebar, the typical connection detail is just you clean the steel, you wrap the wires around and you twist them tight, just like you would for tying rebar together. Because we're dealing with steel angles that are embedded, and in most cases still partially embedded in the concrete, you know, it's not really a practical way to make an electrical connection to them. So we're actually drilling a small hole into the Melan steel using a self-tapping screw and making a connection, an electrical connection that way. And then there's really good QA, QC protocols in the contract, and they're being used on site. So the electrical connections are being checked with a multimeter, and you want to make sure that the resistance in that connection is below a certain threshold. Normally it's less than 1 ohm. Yes.
The wires of that either connection.
Oh, these wires? Those wires are steel wires, stainless steel, actually.
So it's the regular mild steel and the stainless steel wire and then the zinc.
Yes.
And then like, is that stainless steel, like, there's no particular concern that that's gonna go away because it corrodes less than the mild steel?
It corrodes less than the mild steel, and any of the steel that's connected to the anode is going to be protected by the anode itself, right? So, yeah.
And when you use stainless steel versus copper, for instance,
Yeah.
cheaper or?
No, you use stainless steel instead of copper because you want to minimize having a dissimilar metal. So the type of stainless that's in those wires is, I mean, if you want a metallurgy class, it's a very low grade of stainless steel, and the potential difference between that type of steel and normal black steel in chloride-free concrete is virtually zero. If you use copper wires, you have to be very careful about insulating those connections where you're connecting copper. Copper wires are great, they're good conductors, but then when you're connecting between the copper and the steel, you're going to make a dissimilar metal connection there. And if that connection isn't perfectly coated with epoxy, then it's pushing things the other way, because the steel is going to become the anode to that copper wire, right? And then you run into the same thing sometimes if you have like copper grounding systems that are embedded in foundations and things.
Like all of this happens. Terrible.
This is all about electrolysis. This is all electrochemistry. After the repairs, was mentioned already about curing. Most places they're doing wet curing, but on the underside repairs, they're basically putting one application of the actual coating that they're putting on to the concrete as basically a curing membrane. There are areas in between where the physical concrete repairs are, where they're installing these anodes and drilled holes. The anodes that are actually being installed here are a combination of impressed current and galvanic. And they have some benefits because, you know, they still maintain simple installation, but they have a higher level of performance than some of the straight galvanic anodes do. I don't know if we'll see them out on site, but so yeah, anode's going to look like that. You can see a cutaway. Inside this anode, there's actually a battery powered impressed current anode, which is this lower section. And then there's a galvanic anode that's part of it. So when you connect this to the steel and you pour the concrete around, or in this case, you're embedding it in a hole in the concrete, then the impressed current is going to work first. It's going to push more current to the steel because there's a higher driving voltage there. And then when this essentially battery expires, then you're going to be left with the galvanic anode that is continuing to pass a lower level of current. So essentially you pass a higher level of current initially to passivate the steel. And that's a little bit more clear in this graphic here. So the intent is to pass more current initially to passivate the steel. And then you essentially will switch automatically to a lower maintenance level of current to keep the steel from corrosion from reinitiating. So these are going into cored holes. Very short little video here is showing drilling holes. They're about 2-inch diameter hole roughly. And in some cases they're vertical coming down from the top. And on the right, you see there's also situations where they're on the underside of the arch and they're drilling up from the underside. They are staggering the holes on both sides of where the Melan steel is inside to get more uniform protection along the length of the steel that's to be protected. And this video is actually from a different job, but it's just showing you installation. So mortar's already been placed in the hole. He's just buttering up the anode itself with some mortar on the outside. And then you press that into the mortar that's already there until the mortar that's there squeezes down around the anode, fully encapsulates it on basically all the sides. Smoothing out a little bit of the mortar there because it's overhead and you have gravity. He's putting a little wedge in there just to hold the anode in place while that mortar's curing. And so there's a little bit more steps involved in doing things overhead than when you're just doing them down, you know, looking at your feet. Yeah, so we see this. You're then going to make connections to the wires. And you connect the wires together. And then here you can see some of the anodes that are staggered on both sides of the thing. And here they're just filling the top part of after the anodes themselves are grouted into just filling the top part of the hole. And then, okay. Okay, apologize for that. I'm not sure what happened. Some kind of glitch in the internet, but okay, so the metallizing, you're applying a layer. Let me just, so you're basically using this equipment to spray molten zinc onto the concrete surface. And I'm not sure that they're getting set up to do this out on site. When we were there yesterday afternoon, I don't think they'll be spraying when we're there, but you should be able to see the equipment if you're interested in that kind of thing, and certainly the areas. The two primary areas to be metallized are down at the far end of the bridge by span 6, right? And essentially there are some beam ends down there that are to be metallized. And there's this walkway structure that is down basically in the same span. And there's some areas on that walkway structure that they're that are to be metallized. Okay, and you'll see this when we go out there. You need, similar to all of the other cathodic protection or galvanic protection systems, you need to have an electrical connection to the steel. And in this case, normally what you're using is you'll usually drill a hole and install a threaded, tap a threaded rod into the steel in the structure. That'll come out to the surface, and then you'll attach a usually about a 4-inch by 4-inch square section of zinc plate. And that's your electrical connection between this layer of zinc that's on the surface and the reinforcing steel that's inside. Okay. Okay, we've had the opportunity to talk a little bit about the history of the bridge and all of the stuff that went into the design and the project objectives. In this part of, well, actually in Arnie's part and Dan's part, they talked also about the corrosion and the concrete deterioration that's occurred over a little over 100 years. They've talked about the design intent and the methodology. I've talked a little bit about the concrete repair procedures that you're going to see when we go out and do the walkthrough, and some of the different types of corrosion mitigation systems that you're going to see when we do the walkthrough. And I'd just like to close really by just making a couple of comments with regard to sustainability and what I've called here the benefits of bridge preservation. This is probably why I get up every morning and come to work, is because I really believe very strongly that as an industry, you know, you can say the construction industry has a really kind of bad rap. The construction industry overall is responsible for more than 50% of all of the material that ends up in landfill in the United States. And the more that we can do to extend the service life and preserve existing structures, not only keeps stuff out of the landfill, but it also reduces a lot of other environmental things. We don't use up our limited raw materials and resources to simply rebuild things that we already have. We can use those resources to build new bridges and other kind of facilities that we want. There's a lot of embedded energy. And if you think about other ways of measuring environmental impact, like carbon footprint, for example, or other types of pollution and whatever, there's a lot of embedded energy in both concrete and steel. And the amount of concrete, yes, they've replaced the bridge deck, which I think was a prudent thing to do because they want this very long service life here. But the amount of concrete that they have saved by keeping the existing substructure and extending that for another 50 years, it's the amount of embedded energy and carbon footprint that's in there in that quantity of concrete is many, many times the total output that all of us in this room, plus the roughly 200 people that are on the web version of this thing, would put out in an entire year. So by Minnesota DOT keeping this one bridge, that's kind of offset all of the carbon emissions of all of the stuff that we're responsible for. And this is really just one project. I mean, they're doing tons of projects, with Jenny and HNTB, they're involved in lots of different projects. And if we shift what we're doing and spend a little bit more time and effort on preservation, I think overall, we think about our kids, we think about our grandkids, and we want to make sure we leave them something that's sustainable as a world, right? And so just before my very last slide, we're part of a small group, and we have called We Save Structures, and we have an informational website, and there's a lot of stuff in there about sustainability, so feel free to go and take a look if you're interested. One of the things that is there is an online calculator, so you can go online, you can go to the calculator, it's shown on the right-hand side of the slide here. You can enter some details about your specific project in terms of how many cubic yards of concrete are there, blah, blah, blah. And it will calculate, like, how much fresh water is required in order to make that amount of concrete, how much of other kinds of resources are either consumed or would be released in making that. So I think that's quite interesting, and I just wanted to say that near the end here. So I wanted to finish basically by saying thank you very much for your attention. Dan is here, so that's really good. So for those of us that are in the room, we're going to go through a very brief safety orientation, and then we can go and do the walkabout on site, and then we'll come back here for lunch. Are there any questions on this latter part of the presentation? Yes, sir.
What if any of these methodologies can be from new construction?
Okay, so that's a very interesting question. So the question was, what if any of these methodologies can be used in new construction? I would say all of these methodologies can be used in new construction. We don't see them used that often in new construction here, because when you're doing new construction, I would say that you have a lot of flexibility in what you can choose for materials and other options. You can improve the quality of your concrete, you can improve your cover. Those kind of things might get you, you can use more corrosion resistant reinforcing. Those things might get you to your design service life without having to go to the expense of, say, cathodic protection. That being said, we do a lot of projects like this every year in the Middle East that are on brand new construction. It's a very severe corrosive environment, and they know from their own experience that even increasing concrete cover and doing whatever, it just doesn't get them to the service life that they want. We've done the same thing like in Florida, down in the Caribbean, in South Asia, so places that have more high temperature, high chloride, really corrosive environments, some industrial applications as well. But even though it would be nice to say, yeah, we'd like to sell lots and lots and lots of anodes, I think on typical new construction, you can probably get away without having to use this. Now, you might have a situation where you're doing, say, partial new construction, like, and you've got interfaces between where the new and the old is, those are places you might want to still think about. But yeah, it's a very good question. Yes?
So the product you showed that, has a battery that expires after a few months and then capacity is interesting. It's obviously limited in its initial phase by the battery life.
Yep.
These days we have wireless charging technologies, mostly near, but some that go further.
Yeah.
And we're also talking about putting wireless charging into roads to charge cars.
Yeah.
Are you guys looking at all at putting in something in the deck that just continuously drives those batteries forever?
Yeah, we don't have anything commercialized like that, but we're definitely looking at that. Depending on the type of battery that you're using in what I showed here, you're probably looking not so much at, I think you said a couple of months or something. You're probably looking at more like a couple of years, but still it's a limited life, right?
Less than a decade,
definitely less than decades for sure. And it's probably more like 1 to 2 years. But definitely the possibility of recharging is a possibility. There's nothing that's out there commercialized at this point, but that's definitely part of the future.
It's a cost thing.
Sure, it's cost, it's an infrastructure, it's
Probably
things.
feasible, it may not make sense.
Yeah, it may not be economical at the moment.
Related,
Yeah.
just do an outboard battery or plug it into the grid.
You could definitely do that. Impressed current generally is essentially plugged into the grid in most cases. And that can be a very good system. The limitation on those things is just to make sure that you have sufficient maintenance and monitoring, because whenever you have anything that's, connected to the grid or have all this external wiring, you might be a little bit more subject to vandalism, for example. And as long as you're monitoring it, then you're okay. But if you are just kind of putting it there and you don't want to come back for 50 years, in this case, that probably isn't a prudent solution, just because you should be checking those kind of things probably at least a couple times a year.
That's the exact problem we've had at the Illinois DOT, at least in the Chicago area. It's, we put these things in and we
Yeah.
got 2,000 bridges and we leave. And then 10 years later, we come back and it's broken for some reason.
Yeah, and no one knows it. You know, I went and looked at one for Montana DOT 15 years ago. They, oh, yeah, we put in a impressed current system and there was no power to their power supply. I don't know if there ever was, but it certainly wasn't there when, I mean, it was not connected when we were there. And maybe it was for a while and someone decided to disconnect it, or maybe they never ever connected in the first, I don't know. But either way, I mean, technically, those are very good systems. The pipelines, for example, use them widely across all the thing, but they're also mandated by law to do maintenance and monitoring on those systems. And if you're prepared to do the maintenance and monitoring, they're fantastic. If you're not going to maintain or monitor them, then you probably, I mean, it's like putting in the HVAC into this building and then walking away for 10 years and coming back and expecting that the building guy is laughing here because, you know, they expect that you come back here in 10 years and that this mechanical system is still running and the temperature is the way you want and
Well,
everything.
Same with the system and all the bridges. You have natural and unnatural issues that happen.
Oh, lightning, all the wires.
Wire, I mean, it could be, you know, it doesn't have to
Yeah.
necessarily be somebody that walks around with cutters,
Yeah,
but it's a possibility.
no, I live up in Canada, if you haven't figured that out already. No, eh? And we do a lot of work for Ontario Ministry of Transportation. That's what they call the DOTs up there. And they had one whole section of the province. Their district office moved. And no one bothered to notify the power company. Power company was sending their power bills for their impressed current systems to the old office address. And after 2 months or 3 months of them not paying their bill, power company just cut them all off. And they had a moderately effective monitoring system, not as good as it should be. There's a few states in the US that have really good systems, you know, but they did eventually realize that there was no power to all these things. And they realized that the power company, and it's because they were sending the bills to this address where they weren't there anymore and they just got returned no longer at the address, and that was it. The power company turned them all off. So anyway, that's a very good point. Any other questions? Okay, thank you very much for your time. For the people that are online, thank you very much for persevering through our technical difficulty where we lost internet there for a second. And hopefully you got something out of it. If you have any questions for the people online, if you want to leave them in the chat, we will distribute them to the appropriate person so they can get back to you. And I think we will turn off the Teams call. And for the people in the room, we will go through a safety orientation for the walkabout. Okay, so thank you guys.